Now remember back in 11.2 when we first started solving logarithms, it was kind of a basic logarithm such as log 3, x minus 3, 4, and we would just switch it around and solve it. Well, now we're kind of going to add in and say, hey, we're going to actually add some logarithms together and solve. So today we're just getting a little more complicated. We're going to add in those properties that you learned in the last two videos in 11.3. So right away you should say, hey, look, I'm adding two logarithms together. Well, what does that look like? That should be adding, you have the product rule. So if the product rule exists here, we have same base. We're going to do log base 3. I'm going to take x plus 3, and I'm going to multiply it by x minus 3. Still equal to 4, though. So multiplying out, we have log 3, and this is going to be x squared minus 9. You should realize that that's one of those binomials, that they're conjugates of each other, so the linear terms will cancel to 0. Now that I have one single logarithm, I can go ahead and solve this by changing form. So I'm going to take my base is the exponent to the answer. So base 3 to the exponent is x squared minus 9. Now all I have to do to finish this off is use inverse operations. Well, 3 to the 4th ends up being 81. X squared minus 9. Add 9, we get 90 equals x squared. Go ahead, take the square root of both sides. And in this case, we end up with 90 breaking down to 9 and 10. So I end up with x equals 3 square root 10. Now yes, technically you have x equals negative 3 square root 10. But here's where we have our little star down here. Because when we are solving logarithms, you need to check for extraneous solutions. What this really means is that you cannot have a logarithm evaluated at a negative number. So in this case, if I were to put x equals negative 3/10 back in here, I would be evaluating this logarithm at a negative number. So this is no good. I can only end with my answer as x equals 3 root 10. Well, now recall when we had something that had like 2x to the negative 1, or x minus 1, and 8 to the x. We are able to write them with a common base. Well, 2 and 3 have no common base. So if there's no common base here, then we need to actually take the log of both sides. We're going to take log base 10 of both sides to get a log. So we're going to do log of 2x minus 1 equals the logarithm of 3 to the x. Well, hopefully you're realizing, oh hey, there's a power here. I should take that down. So x minus 1 times logarithm of 2 equals x times the logarithm of 3. And yes, we are going to actually distribute this so that we can get x's all on the same side. So distribute log to both. We get x log 2 minus log 2 equals x log 3. Now again, I want the logs on the same side. Or I want the x's on the same side. So I'm going to keep this one positive. I'm going to move this one over. So subtract x log 3. Subtract x log 3. So now I have x log 2 minus x log 3 minus log of 2 equals 0. So I need to get this away from the x's so that I can take a GCF out. So plus log 2 so I end up with x log of 2 minus x log of 3 equals log of 2. Again, I had mentioned I want to take that GCF out. X, I have the log 2 minus log 3 equals log of 2. Now again, hopefully right now another property is screaming at you. Minus, use the quotient rule. So now I'm going to write this as x times log of 2/3. That just helps you make it a lot neater. Equals log 2. Again, I'm going to continue with my inverse operations here to get x alone. So I need to divide both sides by log of 2/3. Now, if this were on a calculator portion of your test, you would end up leaving your answer as x equals log of 2 over log of 2/3. But if it were on a no-calc, if it were on a calculator, you would have to kind of go ahead and say, hey, how do I condense that? Well, hit your logarithm button of 2 divided by log of 2/3. Enter in, you get negative 1.71. So approximately negative 1.71. And in your book, it actually asks you to give it as an exact answer and a decimal approximation. So now we have one more thing to talk about here, is what happens if I'm trying to evaluate something that's not base 10. We've been able to put, hey, log of 5 in your calculator, log of 2,000 in your calculator. Well, if it's not log base 10, we have a formula for that. So we have, if I want to take log of any base A, evaluated at something, say B, that is going to be log, I'm going to write base 10 here even though you never should, of B over log base 10 of A. And that kind of comes from something like this problem here. If they're different bases, it comes from here. In your book, it explains the whole theory behind it if you would like to look it up, but you don't have to. And that's going to be the same thing actually as taking the natural log of B over the natural log of A. You can do either one of those and it'll work. So for example, here we have log base A of B. So put log of 101 on top. So log of 101. And we're going to divide it by log of 4. And again, you have to use your calculator to approximate this. So take log of 101, divide it by log of 4. And we get around 3.3 approximately. Now, I kind of lied. There is a way you can do this in your calculator. Now, on a scientific calculator, you can't. But in graphing calculators, so let's kind of identify this as graphing calculators, there's an option to evaluate this logarithm straight away. If you hit the math key and arrow down a lot to get to this thing that says log base, that means log of any base. So hit it, and it'll go ahead. If you have a fancy calculator, it will go ahead and say, hey, put it here, put it there. If you have one of the older calculators, just follow the directions on screen. So log base 4 of 101, arrow out, and sure enough, we get the same exact answer. So again, on your graphing calculator, if you hit math, and then arrow down to the thing that says log, and then it will say base, this allows your calculator to use any base. No formula necessary. And that's all for the notes for today.